talk about what are the possible defects in two-dimensional carbon structures. So I'm not saying defects in graphene, because graphene by definition is a defect-free single layer of carbon. So let's say defects in two-dimensional carbon. However, we do know that when these graphene-like sheets or graphene layers, when they are present in bulk carbon materials, in that case, especially for example, non-graphitizing carbons, then we know that there is a significant number of non-six-membered rings, and that is in fact responsible for the curvature. That is why we get these curved carbon structures. And when we have a very high curvature, we also sometimes get completely closed structures, for example, fullerene-like structures, which result in the closed porosity of these materials. So we know that these kind of, the six-membered sheets can also contain the non-six-membered rings here and there. Okay. Also, in the case of graphitizing carbons, it's not like graphitizing carbons do not have any defects. Otherwise, we wouldn't have to anneal them out. So we perform the graphitization at very high temperatures. We perform the annealing because we want to get rid of these non-six-membered rings. And that is how we actually increase the diameter of our crystallite. So we increase the La. So we know that in the bulk carbons, as well as sometimes when you're trying to make graphene, you may get these hexagonal carbon sheets which contain non-hexagonal structures. Okay, so these are, this is when we are talking about 2D carbon sheets. And often what happens is when you're manufacturing graphene using the CVD technique, that we have discussed in detail. In the case of CVD fabrication, you will often, it's already very difficult to control, the geometry or the size of your graphene, also the layer thickness. Maybe you will not get single layers, you will get multi-layer graphene, you will get few layer graphene. And in that case, the structures that you obtain often contain a lot of, defects, so to say. Now, whether or not you call them graphene, this material in bulk is actually used for a lot of electronic applications, electrical applications, device fabrication nowadays. So let us discuss what are the possible geometries of these defects. Okay, but also in addition to these geometries, you will find some other geometries as well, but there are certain defects which are sort of more stable than the others. Okay. So let us talk about this. Yeah, one important thing is also that the defects definitely influence the properties of your graphene. Sometimes they introduce, in fact, new chemical reactivity. In principle, your graphene should be relatively inert. But if you have a certain, let's say, unpaired electron, a dangling bond somewhere in the middle, or if you have just nothing but a high energy structure, a structure which has a lot of strain, in that case, you may actually find that your graphene is more reactive compared to the one that does not contain. So that is the actual graphene, the defect-free graphene may not be as reactive. So here and there, people actually introduce defects in order to get certain special type of chemical reactivity. Also, sometimes the grain boundaries in graphene, for example, they lead to a better electrical conductivity, or definitely a different pattern of electrical conductivity along that boundary or dislocation compared to the rest of the structure. So definitely, if you do have some unusual structures in your graphene sheet, you are going to get some unusual properties as well. Okay. Now, let us talk about it this way, that whether or not the defect containing structure should be called graphene, one thing we can definitely assume, or we understand, that graphene is a good model, good experimental model to understand these defects, because defects and the stability of defects and what chemical properties, what new properties will it introduce to your material, these kind of things can be understood theoretically as well as experimentally. Now, if you can actually get single layer graphene structures, for example, by removing them from HOPG, in that case, you can indeed understand, this is a good experimental model for us to understand, what are the kind of defects that can exist in 2D materials. You see, I told you in the past, it was believed that even 2D materials are not stable. Now we know that not only they are stable, they also can contain defects and still be stable. But to what extent these defects should be called defects, and then should be whether or not we should call it graphene after that and not. This is something debatable, but we are just trying to understand the geometry of defects here. So graphene for us is a good experimental model. And what you can also do is you can have a look at this graphene. in your under your transmission electron microscope, also there is something known as scanning tunneling microscope, known as STM. So what you can do is you can see your sample, see the surface, scan your surface of the sample, and some of the very advanced TEM and STM setups, they can actually give you the atomic resolution. So in that case, you can indeed often visualize these defects as well. One very important thing, however, is that your transmission electron microscope, when you're performing the TEM experiment, the beam itself can cause defects. So typically, if you're using a beam of more than 80 kilovolt, in that case, so 80 keV, in that case, you may end up introducing defects even while imaging your sample. So this is also something that you need to know. However, there are transmission electron microscopes that can go down to even 30 kilo electron volts. So in that case, there is a possibility that you can see such defects, or you can really get images of them. Okay, so here is this is some basic descriptions. These kind of defects in hexagonal carbon sheets, graphene-like sheets, they are divided into 5 types, and I have mentioned the names here: stone Wales defects, single vacancy defects, and others. So in general, defects in 3D materials, how are they? So you have point defects, you have line defects, and you also have some defects of 3D nature, like screw dislocation, or you can have some sort of slip plane. So those things are only limited to 3D materials. You're not going to have a stacking fault, for example, in the case of graphene, because it's a single layer, so there's no stacking, there's no question of stacking. Stacking faults of graphite, by the way, we discussed in one of the lectures, and I think you should also go through that lecture if you're if you're interested in this topic, or if you would like to relate the defects in graphene and graphite. I think that's something that you should see. The point here is that some sort of dislocations or defects are not possible in a 2D material, because of the fact that it's 2D. However, what is most prominent in this particular case is the point defects. You also have line defects, so your grain boundaries can be considered line defects. But point defects, number one, just by having any non-6-membered ring, so that you would call a point defect. But sometimes also it's not just one ring that is distorted or that is non-6-membered, but also it's a set of rings. So sometimes it's the defect has a certain geometry which propagates through, let's say it involves 4 hexagonal rings in that sheet. Okay, so you can have these kind of point defects, and then you can have grain boundaries. You can also have add atoms, by the way. You can have carbon add atoms. So on the next couple of slides, I'm actually going to show you some of these pictures of these kind of, or at least the illustrations, the drawings. Okay, so as I mentioned, the line defects are the grain boundaries. But here there is one very interesting thing again. So all of these defects, there are 2 ways of understanding them. One is theoretically, as I said, that if it is for the crystal structure, if it is even possible to contain such a defect, how much energy it adds to your crystal structure. So those are the things that can be understood, theoretically. When you want to understand the defects chemically or experimentally, then you will often perform these chemical reactivity experiments, but that it's very difficult to perform such experiments with single layers. So you will often have this average effect of the entire material. So that is also it's not that easy to obtain. So now what you often end up doing is this TEM STM imaging, and I already told you that one problem with that imaging is that you may end up introducing defects. Another problem is that TEM images are the 2D projections of 3D material, and the entire material, whatever, let's say you have 10 layers of your graphene, 10 sheets of graphene inside your focal plane or within your focal plane. In that case, all of them will look like you will not be able to get any depth perception. So that is why what often happens is that when you see a structure, so they see here is the image again. This was taken, using when we carbonized phenol formaldehyde resin. Okay, so this structure, you see this yellow box I have drawn here. Okay, so this is the point where you see now you could say that this is a grain boundary, or some sort of dislocation, or it also, you may try to analyze, but there is also a possibility that these can be 2 layers stacked on top of each other, because all you see in the case of TEM images of graphene is the edges This is also very important, that you see only the edges and you only see, the one problem is the lack of depth of perception, but also the fact that you see only edges. Or at least that those are the edges are brighter than the rest of the structure, because how transparent our carbon material is transparent to, and especially graphene transparent to optical light, also transparent to electrons. So if it is a single layer, it's really difficult to image it. See the second image of the same location just by changing the focus. Same location. So in this particular case, you see that there's pretty much nothing visible, right? It's the exact same location. And this is just by playing with the focus of your imaging. So this can also happen. There is a high probability that you have something like this. The structure actually is not even just one layer, but it's there are 2 layers of graphene. Okay, so there are you need to be very careful when you are performing TEM imaging, and when you recognize and say that, oh, this is a defect or this is a grain boundary, then you need to be very especially careful, because you may not be able to you need to make sure that your interpretation of the TEM images is correct, and you need to you need to perform the imaging also in various ways, just by changing the focus, changing the location, to ensure that what you're doing is correct. Okay, so other than these potential defects, there are also the edge symmetries sometimes that are broken. So what do I mean? I think I told you, I don't know. The edges can be either zigzag, or armchair type. So these are the two acceptable sort of configurations for the edges of graphene layers. But often so this is one more additional type of defect that you have. At the edges you have a little bit of very strange structure. Sometimes one atom is just so that it's like what can I say, rough edges. So they do not have any specific type of symmetry, but they have some other type of structure, which again makes also them more chemically reactive. Already the edges of graphene have dangling bonds, because there is no termination, so to say. So you have dangling bonds there already, and sometimes if the structure is also not according to these two symmetric arrangements, in that case you can also have higher reactivity along the edges of graphene. So that can also be considered a defect. Okay, so now let us see some of these images as I told you. Okay, so here on this slide you can see 5 types of defects in graphene. All of them are point defects. Okay, so the first one is the stone vales type of defect. Now I don't know how clear it is, but I hope you can see that there are 4 graphene layers which are involved. 4 hexagonal sheets, rings that are involved in this defect. Okay. Now here you see there are 2 rings that are involved in this defect. Okay, in this particular case, this is kind of an interesting structure. There you have an add atom, so you have an additional carbon atom here. Okay, so these kind of defects you know in the context of 3D materials, or are usually even when you perform doping and you have interstitial atoms. So something similar, but this is number one, we have no foreign element, but only, so all the defects that we talked about are the defects without the addition of any foreign atom, but it is just a carbon atom which has been during its formation it somehow arranged itself in a certain position, and then maybe afterwards there was no not enough energy for it to anneal out or to form a standard hexagonal type structure. So that particular atom then now stays there. Okay, so this is the add atom vacancy. Here you can see that there are these 4 rings that are involved in this particular type of defect. So these are called double vacancy defects, and they are of different types. So here you can say even more than 4. There are multiple rings that are involved in the formation of these defects. Okay, so these are some of the point defects. Okay. So now let us talk about the line defects. So you see this T-like structure. I have shown the direction of the Burgers vector here. Okay. So you can see that you have also, certain type of line. So when the there is often the line defects actually propagate from various, or they are a connection of various point defects. So if there is one point defect here and then here and then here and then here, all together you can call it a line defect. Or often for the entire structure to gain at least a slightly lower energy state, it will try these defects, the point defects will try to connect with each other and form a line defects that is still slightly lower energy, or it's a more preferred configuration. Okay, so here on this particular slide you can see there are all these different line defects or dislocations which ultimately lead to the formation of a grain boundary in graphene-like structures. Okay, so after discussing all of this, now we are moving on to some notations again related to the crystal, because this is important for graphene and also for carbon nanotubes and in some other things that we are going to learn in our coming classes. Okay, so now what we are going to talk about is known as the NM notations. So NM notations are very important because these are basically, this is a method of describing a certain location on a graphene crystal. This becomes even more important when we talk about, let's say, carbon nanotubes. If you remember in the beginning of the graphene lecture, I told you that if you fold the graphene sheet, then you get carbon nanotubes. That is not really chemically true. It's not like, this is the method of preparing carbon nanotubes or something. But why do we say that? We say that because, this is the way of describing the crystal structure or a position of any certain atom on a graphene sheet, which accordingly will also define, the orientation of your carbon nanotube. So you probably also remember that if you had, zigzag type of carbon nanotube, so the ends at the, of the carbon nanotube. So for example, if you have something that looks like this, then in that case this is your zigzag type carbon nanotube. And if you have some sort of this kind of structure towards the ends, then this is your armchair type of carbon nanotube. So if basically to define the the axis of your carbon nanotube and to define the orientation, then also you use the NM notations, but I'm actually describing it here because NM notations are also occasionally used for understanding the defect in graphene. So if you want to tell somebody that, okay, this is where my graphene, the defect is, or a non-6 membered ring is situated at this location, then you're going to give NM coordinate, that this is the position. Okay, so let us talk about this. So this is actually something very simple. If you take your lattice along your, somewhere on your graphene sheet, then whatever, you have two lattice vectors, right? A1 and A2. So along A1, whatever distance you need to travel from the origin, that is known as N, and along A2, whatever distance you travel is known as M. Actually, N and M are also exchangeable. So A1 can be associated with M and A2 can be associated with N. There are also a few other things in the graphene crystal that are allowed, which are actually otherwise in many other types of crystals that is not allowed. So for example, how do you take your primitive unit cell? So if you remember, what we have discussed previously is something like this. So this is how we take our primitive unit cell. So we have two atoms, A and B. These are not equivalent, you know that. And this is one way of, this is basically the usual method of considering the unit cell of graphene. But it is also possible to take your unit cell like this, because this actually does not change anything. You still have two atoms. And this is basically, even the size of your, the length of your vectors and the direction of your vectors does not quite change. So in that case also, this is one more allowed configuration. What is also allowed, interestingly, is that you can change the angle. So for example, you can also take this particular rhombus as your unit cell. So why can I choose this as my unit cell? Because if you think about it, your graphene sheet it's made of hexagons, and these are symmetric hexagons. So they all have 6-fold symmetry. You can rotate your entire graphene sheet in any way. So you can actually also choose any point as your origin. I mean, in this particular case, when I'm going to describe the NM notations, I'll take this particular point. But all A sites can be exchanged with any atom that is of A type can be exchanged with any other. When I say exchange, that means the location. I can choose any of my A atoms as my origin or any of B atoms as my origin. The only thing that I need to keep in mind is that A and B type atoms are not equivalent. And again, it's nothing to do with the chemical structure, but the fact that they are, they do not have the same types of bonds surrounding them, or their neighbors are not the same. So anyway, A and B, that you know already, are the two types of neighbors. Okay, so now coming again back to the NM notation. So if I have, let's say this is my, this is the one that I have selected as my crystal lattice. Now I have this vector, let's say A1, and this is my A2 vector. You know that these are at 60 degrees. They are not at 90 degrees, so this is not a Cartesian system. Okay. So, well, now what I need to do, I take one point, any one point here, say, on top. And this is what I need to define. What are the coordinates of this given point? Okay. So now what I'm going to do is I'm going to see how far do I need to, travel from my whatever atom I have selected as my origin. Okay. So this is my origin and this is the vector. Now you can see here that how many, how much distance did you travel? 1 time A1, 2 times 3, and 4 times A1. So this is my 4. And of course, we have not, covered any distance along A2. So that is 0. So this is as simple as that. This is my 4, 0 point. Now when I talk about carbon nanotube fabrication using, so if I take the same graphene sheet and I roll it up, okay, then what happens? Now this given 4, 0 point and my 0, 0 point should overlap. Only then we will, get a complete tube. Okay. So if 4, 0 and 0, 0, they are overlapping, in that case, this vector, this entire long vector that I have defined here, this vector basically becomes your periphery or your circumference of your tube. So basically, this is the circumference, and this vector, in fact, is often called either circumference or chiral vector. So when we talk about the carbon nanotubes, then we are going to talk what is chiral and what is achiral. But the idea here is this is called the chiral vector, and this is denoted by C. Okay, so sometimes it's called circumferential and sometimes chiral, but what does it mean? Sometimes also you will have another vector that is, that is known as the axis vector, because obviously this is the axis of your carbon nanotube when you're rolling up this graphene sheet. Okay, so now one thing from here you understand is that when you have zigzag type of carbon nanotubes, then the coordinates are going to be N0 type. Okay, because you're always going to have this kind of configuration. So N0, if somebody gives you that my carbon nanotube is 10-0, that basically means that it is you already know that this is a zigzag type of carbon nanotube. Okay, so now we will talk about the other type, the armchair type of carbon nanotube. Actually, armchair type of symmetry, or how to define that location. This is important for us also on the graphene sheet, irrespective of where do we define it. Okay, fine. So this is again my graphene sheet. Okay, what I'm going to do here is I'm going to also add one more set of hexagons. And the reason for that is that when I talk about the armchair symmetry, unlike when I was talking about zigzag, in the case of armchair, it is always good to have even numbers when we are talking about, when we are describing the structure. So, for example, when I take my lattice now, I will choose this lattice, this here. Okay, this is my lattice. And I'm selecting this because it is parallel. It is in the direction of the point that I want to describe. And this is going to be my point that I'm going to describe is this one. Okay, so the idea is to take the lattice such that it is you're in the parallel direction. Okay, so in this direction I take the lattice, and then now I want to if you want to redraw the lattice, number 1, 2, and 3 and 4. Okay, now here I am. Why did I? So you see that in each lattice I'm covering sort of 2 hexagons, unlike in the case of zigzag, where I was covering only 1 hexagon. So it is then easier to define it for a certain point, your NM location, where you have, you know, the even number of hexagons covered. Okay, so now let us see how do we do that. Okay, so again, this is going to be my origin. Now how much? So I have this point, this lattice vector as my A1, and this is A2. Okay, how do I get to A1 and A2? So if I want to reach this given point, then how much distance I need to travel along A1? That is 1 times. But how much along A2? Well, this vector here, if you see that this is also equivalent to A2 vector, neither the direction nor the magnitude is changing. So I can also call this, and you know, this is a similar vector. Okay, so now if you will see, I travel, you know, one times along A1 and then another 1 time along A2. Similarly over here, A1 and then A2. So the coordinates of this point are going to be 2 times A1 and 2 times A2. Okay, so this is, if you have this kind of, I described it like this, and I was also taking the this point here rather than this point, because I wanted to describe that if you have this NN type of carbon nanotube, when we talk about tubes, in that case what you're going to get is the armchair symmetry in your carbon nanotube. So you will, when you have the armchair symmetry, you will always have these sort of 2 or 3. So this does not like just end at half. So you will not have a carbon nanotube which is like this. Okay, so you will sort of complete this armchair or armchair geometry, and that is why we took this rather than 1.5 hexagon, we took, or it's not 1.5 hexagon, it's actually 3 hexagons. So you don't take 3 hexagons, but you take 4, because you also want to have this entire thing completed, the armchair completed. This is actually, this very structure is known as armchair, this structure, because if you will see it, it actually looks like the something like a chair. Okay, so this is the second type. So now we understand what is the NN or N0 type notation. Now the third one is where you describe a chiral type carbon nanotube, and when we talk about in the context of graphene, then we talk about a certain point which cannot be described just by using either armchair or zigzag type of notation or calculations like how we did it. So this is the third one. This is called a chiral type. When we make a tube out of it, then we call it chiral. Basically it is neither this neither of these two symmetry. Okay, so this is our third situation. I have selected some point here. Okay, this point, if I if I try to draw a vector from my origin, then you will see that it's really difficult to reach this point just by using either zigzag or your the armchair type symmetry. Okay, so how do we calculate? What we basically need to do is we need to see how do we reach this atom. Okay, so what is the possible path? Is this the possible path? Okay, in that case you may not be able to, you will just reach this point here. Okay, but you will not be able to reach the origin. So then we will probably also need to follow some other path. So let us again go back to first selecting our lattice here. Okay, and then again the same way we have our lattice vectors, which are A1 and A2. Okay, now how much do we travel to, or how do we get to, how do we reach this point? So there is one also option that we travel along this and this here. So basically 1 time A1 and 1 time A2, that is simple. So 1 time A1, and this vector again is our A2. So 1 time A1, 1 time A2, we reach this point, and then from here, if we had the other type of unit cell or unit cell, then we could have just walked in this direction 2 times. And this, you also know that it is equal to A1. This distance, that this is equal to, because this was the, when we were drawing the N0 type of structure, in that case also we saw that if we took the lattice vector, lattice somewhere here, then this was also equal to A1. Okay, so now you know that 2 times if you travel along A1, and here this was one more time along A1. So in this this one here, okay, so we traveled once along A1, twice along A1, and 3 times along A1. So our A1 coordinate becomes 3, and A2 we have traveled once. Now you have 3, 1 as the coordinates of this point. What this means is this is something called NM. So now you don't have NN type. Also, you don't have N0 type of point. Now what you have is NM type of point. And if you draw a carbon nanotube, then you're going to get neither zigzag nor armchair type symmetry. It is going to be kind of any random mixture of these two types of positions. And in that case, what you will call it? You will call it the chiral type of carbon nanotube.